And let's open that. And let's open that. All right, we are recording. We don't quite have good projection yet, but it's on its way. Before we get going on that, let's see, I think actually I need to be a little bit earlier. We'll go right there. Any questions on anything we've done so far, anything about the course, as you've been going back and reviewing the syllabus and the research paper and all those things that you read, okay, and that we went over? Any questions? Everybody is up to speed. And remember, everything I think, I just remembered something, but not this class, but another class. I've got to change something on Blackboard. I found out I put the wrong syllabus in the wrong class, so I've got to change that, but that wasn't this class, it was a different one. All right, any questions? None? Well, then I believe we're starting on page 54. We're chapter 1, limits and their properties, 1.2, finding limits graphically and numerically, and we're on example 4 at the bottom of page 54 for those who have the text already. Okay. Books seem to love this kind of problem, and I think it's almost ridiculous problem to even bring up, but I guess there's a reason they bring it up. It says, discuss the existence of this limit. The limit as x approaches 0 of 1 over x squared. What's the limit of that as... No, I'm sorry, this is not the ridiculous one I thought they brought up, but let's say, so what do you think of this? What's the limit there? Do we remember limits? I mean, it was a long time ago, 2 days, okay? What's your thoughts? First impressions. What would be your guess? Anybody? Out of the blue, something. What's your feeling on it? Remember, I said there were sort of 2 forms for certain types of problems, especially since x is going to 0. One of those forms was when you have 0 over 0, and we called that an, that was a long time ago, indeterminate form. Those indeterminate forms may or may not have limits, okay? Is this one of those forms? No. What kind of form is this? Something other than 0 over 0. And what's always the answer on that? Undefined. No way you can do it. Does not exist. Okay? Now, there are some later places in maybe this book or other books, they'll say, we'll call this going to positive infinity. What is positive infinity? It's not a number, okay? It doesn't exist. I mean, it just keeps going. It goes infinitely large, whether you approach it from the right, left, or from the right. 1 over x squared gets, as x approaches 0 from the left, that's getting... This is going to 0 very quickly, and 1 over 0 is undefined, okay? Very large number, extremely fast, positive, and from the right, same deal, because you're squaring that. So this does not exist, okay? And perhaps this is the reason they did 1 over x squared. If you did 1 over x, they're going like this. One's going south and one's going north as x is approaching 0. So that obviously doesn't exist, but this doesn't exist either. Nowhere in sight. Okay? And, all right, they don't do any, I don't have it on the PowerPoint. They just give a few examples of when x is approaching, when x is equal to, let's see. Okay. When you choose x even 1/10, this will be 1 over 100th, 1 over, let's see, 1/10, okay. 1/10 squared would be 100th. 1 over 100th is 100, okay. And then get a little closer, 1 over 1,000. Whoa, 4 zeros after it. That'd be 10,000. You know, 1 over, if x is, 10,000, then you have 8 zeros after it. It just gets enormously large very quickly the closer you get to 0. So there is no limit. The limit does not exist. And I don't know. That's all there is to do that. It doesn't exist. Anytime you see something over 0 and that something is not 0, it's not going to exist. So don't even bother with it. Okay. There's one more here, and this is example 5. Now, I think I mentioned to you before, I'm going to go and erase this one because there wasn't much to do on that. It just doesn't exist. Okay? And this is the one, okay, I was jumping ahead. This is the one they love to ask questions about, and to me it's still sort of a ridiculous thing even to think about. But here's what it is. Discuss the limit of, I just love the way they say it. Discuss the existence of the limit. Okay, just say it once. Limit as x approaches in 0, okay, of sine of 1 over x, okay? And they make a sort of a big deal about this, and there really isn't much of a deal to make about it, because guess what? That form is undefined. But they like to say, oh, but when you take the sine of that, well, look, if it's undefined, do it. Sure, the sine function, and this gets very large, right? Okay, as x approaches 0. It would, x is 10, 1/10, that's 10. And sine of 10 is whatever. And then sine of 100, sine of, this number gets very large as x approaches 0, either from the left or from the right. But the sine, sure, it stays between plus or minus 1. But that's all it does, is just oscillate between plus and minus 1. And the larger the number is, negative number or positive number, it doesn't matter. It just sits there and oscillates between plus or minus 1. And that's why they call it oscillating behavior, as the title of this one. And by the way, I started to say, this is also located at larsoncalculus.com. You can go to that website and see, say, a fuller description of this. Okay? Now, I see some people are looking at, you got your book? Okay. It's the ebook. Okay. So you didn't need a code to get it. I mean, you needed the code from the bookstore, but you didn't need a code from me. Is that right?
The only thing you need a code for is if you want to get a print option, like if you want to rent it.
Oh, then you need the WebAssign code. Yeah. Are any of you waiting on that? Would like to get that? And those are cheap, like $8 or something like that. So if you do it, I don't know. Probably Friday is the earliest I'll be able to get in touch with Cengage to see if they can get that ball rolling. Okay. But here, this is undefined. And taking the sign of an undefined number doesn't make it defined, okay? It's just not. But they love to ask examples like this. The difference here is, even though that's an undefined number, the sign of a number stays between plus or minus 1, and it just gets faster and faster and faster the closer you get to 0, either from the left or from the right, but it never approaches anything, because 1 over x is not approaching anything. So it can't. So that's limit doesn't exist. All right, now we're ready for this slide. Common types of behavior associated with non-existence of a limit. 3 things. F approaches a different number from the right side of C than it does from the left side. If that happens, the limit doesn't exist. It can't exist, okay? If it's approaching, we did the absolute value of x over x, okay? Approach -1 from the left, it approach positive from the right. Never the twain do meet, so can't have a limit then, okay? Now, secondly, F increases or decreases while bound as x approaches C. That would be the example of 1 over x squared, 1 over x, anything like this. There is no limit. It's going to infinity, you might say. Okay? Or F oscillates between 2 fixed values as x approaches C. And it just oscillates faster and faster and faster, but never goes there. Usually that's the case when the argument of the outer function is undefined. It's just increasing without bound. And it just makes the function go up and down like the one we just saw. Okay, so that's sort of a recap of what we finished with last time and hit on today. All right, now they throw this one in here. And I've tried, it's in the text, but it's not on the slide set. So let me hit it just for completeness sake. In addition to the limit of f of x equals sine of 1 over x, there are many other interesting functions, if you call them interesting, that have unusual limit behavior. An often cited one is the Dirichlet, or Dirichlet, I think is how I would pronounce it. The trouble is, he was German. If that was French, I would say it was Dirichlet. Now, maybe his ancestry was French, and they did call it that, but knowing the Germans, they probably called it Dirichlet, okay, because they wouldn't do the other. Let me see if I can recall. Taylor, is that right? No, sorry.
Elise.
Second?
Elise.
Elise, got it. That was going to be my next guess. Okay, got it. Okay. Now, he came up with this function. Now, the little blurb under his name says, in the early development of calculus, definition of function was much more restricted than it is today, and functions such as Dirichlet or Dirichlet function would not have been considered. I think I'm with them, because I don't consider this a very reasonable function at all, but I guess technically it is. F of x is equal to piecewise defined function, 0 if x is rational, and 1 if x is irrational. Okay? Yay! What a clever little function that is. Can anyone think of a usefulness for that function? I can't. I'm sorry. I just cannot think of anything that could be good for unless you're just trying to separate numbers. You have irrational and rational, and all those with 0 are rational. You know, but frankly, who cares? I mean, I don't know. I shouldn't be negative. There may be a very good reason to have such a function. Y'all think you could graph that function for me? My best guess of how that function would graph would be this. Okay? Guess what? There's an infinite number of rational numbers in between any 2 pixels on the page here, and there's an infinite number of irrational numbers between any 2 pixels on the screen. So how in the world would you graph that thing? It would just be... So what's the point? I don't know. Okay? But it is a function by this current definition. All right. Let me see if I can recall. Is it Devin? No. Huh? Anthony. Yeah, I already have Devin. Okay. Sorry. Anthony. I left a space for you. Okay, there you are. Anyone else come in since I called roll? All right, good deal. So you've seen it. Yay. If anyone wants to write on Dirichlet formula and convince me of what great uses it has, sock it to me, okay? I'd love to know what use it has, or who he was, or anything else about him. All right, that done, let's move to a formal definition of a limit, okay? I guess this is just a change of the way they do things, but back when I was in college, and that was within the last millennia or sometime like that. So this is where we began. We didn't do these other things. I didn't really like it that much, but this is, I mean, the professor had us, we could sing-song this in our sleep. Whether we knew what we were talking about or not, we could do it. But here's the formal definition of a limit, okay? Let's take another look. Okay, now we're going to start with that informal definition. If x becomes arbitrarily close, remember those weasel words there, to a single number L as x approaches c from either side of c, then the limit of f of x as x approaches c is L. Remember, it has to approach it from both sides, the same limit, however you're doing that. And this is then what we say, the limit as x approaches c of f of x is that limit L. At first glance, that definition looks fairly technical, if you ignore the arbitrarily close, okay? But even so, it's informal because the exact meanings have not been given to the phrases arbitrarily close to L. Okay? What's that? Oh, L being a number, yeah, a constant. Some number, L, some value, okay? Not infinity, okay? Has to be a fixed value, exactly. Now, the other one as x approaches c. Well, what do we mean by that? You know, that's a little bit less ambiguous than arbitrarily close, but it's still not well defined, okay? Now, remember, I don't think either Newton or Leibniz were really bothered by this kind of stuff. It's only later mathematicians that this isn't rigorous enough. You know, you have to get more rigorous definition here. So here's what we're going. The first person to assign a mathematically rigorous meaning to those two phrases was, I don't know if I'm going to pronounce it right, Augustin Louis Cauchy, I don't know how you pronounce it. And he uses this epsilon delta definition as the standard. And we remember the delta showed up a little earlier. We hadn't seen the epsilon, but I mentioned the epsilon. And that's what we use today for the definition of a limit, the formal definition. So here's how basically it goes. If you look at this figure, okay, now this is a really, well, actually, I first looked at it, thought it was a straight line, but it's not. It's actually a curve, okay? I don't know exactly what function it is, but that really doesn't matter here. It's the graph of a function, okay? Now, let epsilon, okay, and this is the lowercase for epsilon, the Greek letter epsilon, like our letter E, represent a small positive number, okay? Now, I can to this day remember Dr. Osborne saying, and this is how you started everything, let epsilon be greater than 0, okay? That's how he started, okay? And we had to do that. I knew that, whether I knew what epsilon meant or anything else, I knew you had to say those words. Let epsilon be greater than 0. It has to be positive. That's all that's saying. What we're understanding is also small. Then the phrase x becomes arbitrarily close to L means that, okay, f of x lies in the interval between L minus epsilon and L plus epsilon. So if this is the limit, and the thing that's a little weird here, we act like we know what the limit is, and then we go about saying how we find it's the limit, which kind of seems backwards to me, but it's okay. Okay, epsilon is some small positive number, so x plus epsilon is going to be greater than L, and x minus epsilon is going to be less than L, because epsilon is positive. So basically that gives you a bracket here, okay? So the phrase f of x becomes arbitrarily close to L means that f of x has a lie in the interval around that value L, okay? So it has to be within that L plus epsilon and L minus epsilon, or L minus epsilon and L plus epsilon. Okay, that's just the first part of it. That's the arbitrarily close. That supposedly cleans that up for you. Okay? Now, the next part of that says, as x approaches c. Okay? What that means, there is some delta also greater than 0. Okay? Small number delta greater than 0, such that c is in between c minus delta and c plus delta, of course. If delta is a little positive number, c's got to be in between that. So if you are given any epsilon greater than 0, no matter how tiny you make it, okay, there you can find a delta. This is if the limit exists, a delta small enough so that you can guarantee that if you're close enough to c, this is what the delta gives you, you're going to be the f of c minus delta, f of c plus delta is going to lie within epsilon of your limit. Okay? So that means if you choose an epsilon incredibly small, you can find a delta, but you can't find one that is going to guarantee you stay between those epsilons. That's what the formal definition does for you. Okay? It just introduces these things to tell you what arbitrarily close to and as it approaches. That's what it's doing. Okay? So let's see how you put all that together. So one way to say arbitrarily close is this. The absolute value of the difference between f of x and L has to be less than that epsilon. Why absolute value? We said epsilon was positive, right? So if you didn't do an absolute value and f of x was 0 and L was minus 4 million, okay, yeah, that would be less than epsilon because 0 minus 4 million is certainly less. No, you say no matter which side of L you're on, f of x would be above or below, the absolute value of the difference is less than that arbitrarily small epsilon that you chose to begin with. Similar to the phrase, and this I already talked about because they had it on the graph, x approaches c means that there is some positive number delta, a delta greater than 0, such that x lies either between c minus delta and c, or between c and c plus delta. So why don't they just say it lies between c minus delta and c plus delta? Things like that feel like that. This fact can be concisely expressed by the double inequality that 0 is less than or equal to the difference between x and c. You see, this is how close c is to x. Your variable is to x. That's got to be less than delta. Okay? Now, of course, notice they don't put the 0 less than this. Well, it's an absolute value. You know that 0 is going to be less than an absolute value or equal to. This says you don't even have equal to. In other words, x can't equal c. That you can get as close to c as you want with x, but you can't make it equal to c because then that would be equal to 0. It's still going to be less than delta. So this is almost the same type situation here. It's just that this one, the difference here could actually be 0. There, you don't require x equals c. You're just getting close and close to c. That's because sometimes, in a lot of these that you're interested in, it can't equal c because that would make a 0 in the denominator. But the limit can still exist if it's an indeterminate form. Okay. Now, that first inequality, this one is what they talk about. Here's two inequality. They call it a double inequality. So they're doing this one first, and then they'll talk about this one. Okay? So, the first inequality, 0 less than or equal to that, the distance between x and c is more than 0. That means x can't equal c, or it may be that x can't equal c. The second inequality says that x minus c is within delta units of c. Okay, that x is within delta units of c. That means you're close to c. Okay, can't be on c, but it can be very close. And it says that x is the distance within, the x is within a distance delta of the value c. Okay, about 10 ways to say it. So, here is then the formal definition of the limit. Okay, we never used to say this first part. Let f be a function defined on an open interval containing c. Now, what do we mean by open interval? The endpoints are not necessarily part of the interval. Everything in between. A closed interval, the endpoints would be considered. Okay? Semi-closed one could be open. Okay. So an open interval containing c, except possibly at c. F doesn't have to be defined at c. It could be, but it doesn't have to be. That's why we leave off the equal 0 on it. Okay? But f is a function defined everywhere in the open interval containing c, and let L be a real number, like you were saying before. L is some number, a constant. Okay? Then the statement, the limit as x approaches c of f of x equal L, that means that for any epsilon you choose, no matter how tiny you choose it, as long as it's greater than 0, okay, there does exist some delta also greater than 0. It may be incredibly small itself, such that if the delta, if the x minus c, if x is close enough to c to be, it can't be equal to c, so that's why we don't include 0, but it's within delta units of c, then you guarantee that the absolute value of f of x minus L is less than epsilon. Okay? So what is that saying? No matter how small you choose the epsilon, you can therefore find the delta, which makes this statement true. Okay? That's the formal definition. That takes the arbitrarily close and as it approaches out of it. This gives a formal meaning to that. Thank you, Koshi, for bringing this on us. Okay, we really appreciate it. Okay, now example 6 is in your text, so let's hit it. Given the limit as x approaches 3 of 2x minus 5, we know that's equal to 1. Okay? Yay. Okay? Now, frankly, practically, what we'll do when we're doing limits, the first thing you always do is just like Glade. You plug it in, see if it works. Okay? Now, when you plug it in, if you get something like 7 over 0, you know it's not going to work. Okay? If you plug it in and get the square root of a negative 3, you know it's not going to work. If you plug it in and you get the log of a negative 7 or a log of 0, you know it's not going to work because those things are undefined. Okay? But if you plug it in and you get a number, guess what? That is your limit. Okay. Let me make a guess here. Taylor? All right. Still writing on the original form, and I've had names squeezed in between the other names. And the problem with that is they're still canceling classes. I don't know why they are, but they are, so then students could be moving around, so I can't do the formal grade book until they get that finished. Okay? But guess what? They don't want us to just plug it in here. If you do, you see that's the limit. No sweatskis, and you're through. But they want you to use the formal definition. Find some delta, some positive number delta, such that the absolute value of your function minus what you're saying the limit is, which you know that is it, is less than, they've chosen an epsilon of 0.01, okay? And it says whenever 0 is less than absolute value of x minus 3 is less than delta, okay? Now, you're looking for a delta. All right. So, guess what we're going to do, folks? We're going to monkey with this sum and see if we can get it to look like that. Okay? That's not a very formal math definition, monkey with it, but let's see what we can do. All right. So this will be 2x minus 5 minus 1, right? Less than 0.01. Everybody agreed? Okay. Then we'll take the absolute value of, well, let's combine like terms inside there. That would be 2x minus 6, less than 0.01. Okay, pretty good so far. What can we do here? 2x minus 6. What's the F word? Oh, wait, y'all, okay, so not everybody's been in my class before. Some of you have. Okay. In my classes, the F word is factor. Okay, so wipe your dirty minds away. Okay, not dealing with anything else. The F word is factor. Okay, now if that's offensive to anybody, I won't use it. Are y'all okay with it? Okay, all right. So what can we do here? Take out a 2, and that leaves you with x minus 3. And that's less than 0.01. Hey, I can pull that 2 outside the absolute value bars because it's positive, right? So let's do that. 2 times the absolute value of x minus 3. See, the x minus 3 may still be negative, so I can't pull it out. Less than 0.01. Remember what we're trying to get? That, okay? Well, guess what? We can divide both sides by 2, okay? Those go away, and now we have the absolute value of x minus 3 is less than 0.005. There's the delta. And by the way, since it's the absolute value, we'll require that to be less than 0. In other words, x can't equal 3, okay? We know it can. We plugged it in, and it was okay. But we're just going to say, no, we're not going to let x equal 3. So there we have it. We found our delta. There it is, 0.005. Okay? Now, you might say, oh, these limits aren't bad, are they? Okay? Well, when it's one that's obvious like this, you can usually do it just this simply. It's the ones that are obvious that really get messy. They're not all going to be this easy to do. Only the obvious ones will be that easy to do. Okay? Okay, I kind of did it probably the same way they did in the book. We'll see. We'll let them show that to us. All right, for me to erase this? Okay, and we'll see how they did it. See if I left off any critical steps. In this problem, we're looking for, you're working with a given value of epsilon. There it is. That was your epsilon. You know, the absolute value of the function minus the limit, that's going to be your epsilon, less than epsilon. So we know what the epsilon is. Okay? Now we want to monkey with that, deal with that until we can get this to look like that. Okay? We're trying to establish a connection between this, which we know what it is, and that which we are trying to determine what delta that would be. So, sock it to it. See what we can do. And they did the same thing we did. Remove the parentheses. Factor out the 2 because it's positive. It can come outside the absolute value bars. And then because that inequality is equivalent to this inequality, you can choose delta to be, divide this by 2, so that looks like that, and sure enough, you get 0.005. Does that make sense? Now, it seems maybe incredibly useful, easy to do. Don't worry, most of them are not. Some of them are not. But the good news is we're not going to use the formal definition past where we have to. After a while, we'll find other techniques for doing limits. So this choice works because 0 is certainly less than, you can make 0 less than this, but just not allow x to equal 3. So then 0 would be less than that, and this thing, because of this, would be less than 0.005. So therefore, you found your delta, and that implies that everything else is true. And really, it's very circular, okay? You're going back, plugging this in, and shows that it indeed is less than your epsilon to begin with. That drives me nuts, because I think, why are we doing this again? Because that's where we got it from, so it better work, okay? But they like to do that. Okay, and then graphically, here's what we're saying. Here's the line here. Don't write it anymore. Oh, there it is, yeah. 2x minus 5. Okay? That's a straight line. You know it has a limit. There it is. No sweatskis here. But what they're going to do is pick an epsilon greater than 0, or O1 below or O1 above that 1. So your f of x is going to be between these two. Guaranteed. You want it within those two. Epsilon. Well, guess what? The slope here is 2, so you're going to have to divide that to get within there. And so therefore, anytime you're within 2.995 and 3.005, you can guarantee your answer is going to be there. Okay? This is a straight line. It makes it pretty obvious that way. Okay. Can't think of anything else we can do. Any questions on that? Formal definition. That's what you're aiming for, is to reproduce, find the delta given the epsilon. Okay? Now, that is so you have numbers. Most of the time, they like to do it abstractly. So let's see. Whoa, yuck. They show you on the slide set, and this is pretty common, the easy ones, okay? They don't show you the more difficult ones. So here's example, or more involved one, I'll put it that way. Example 7. Using the epsilon delta definition of limit. Use the epsilon definition of a limit to prove that the limit as x approaches 2 of 3x minus 2 is equal to 4. Okay? Now this time they don't give us, I don't believe, yeah. They don't give us, you want it within such a tolerance, you might say. You know, you don't, they're just saying prove that's true. Okay? Now later, what we're going to do, what is my first rule? Glade. Plug it in, okay? 3 times 2 is 6 minus 2 is 4. That's what we're going to do in the future. Now we're using the epsilon delta definition. So what that is, and this is how, almost from memory, let epsilon be some small number, not that small, be greater than 0. I put the wrong symbol there. Epsilon be greater than 0. And you can get it as small as you want to, folks. You get to choose that. Then, there exists, I'll say is, a delta, also greater than 0, such that, let me write it out, such that for any, see, how is a better way, which is better to put first? Yeah, they put the delta first, such that 0 less than absolute value of, and here you go to this part, x minus 2, and it really doesn't matter which order you write them because it's absolute value, is less than delta, okay, anytime the absolute value of 3x minus 2 minus 4, that's the function minus the limit, is less than epsilon. Okay. Now I said this was more complicated. It's not. This one's just as easy as the last one. In fact, we'll do the same thing. So what would you suggest we do first? We don't know what epsilon is. The last time they told us. This time we're just going to leave it as epsilon. Okay? Let epsilon be greater than 0. We've got to find the delta. That's what we're doing, finding the delta. There it is. No, never mind. Okay. So how do you do this? Pretty easy. Help me. Okay, 3x minus 2 minus 4 less than, absolute value, less than epsilon, and then combine like terms, absolute value of 3x minus 6 less than epsilon, factor out a 3 times the absolute value of x minus 2 less than epsilon. Help me. It almost looks like that. What do we need to do? Divide by 3. Okay? And then you can just put the less than 0 here. That goes away. There you found it. For any epsilon you choose, as tiny as you want it to be, 1/10,000,000th. Okay? If you want epsilon that small, and you want to guarantee that this function is within that distance of 4, all you have to do, if you choose that, is take a third of that 1/10,000,000th, and that delta will work for you every time. Okay? That's the formal definition. No matter how close you want to get to, how small you want that tolerance to be, you can find a delta. Now, there may be ones that you can't find a delta, and if so, they don't have a limit. But this one does. And that limit, no matter how small you make the epsilon, take a third of it, and you've got a delta that works. Okay? You've just done the formal definition of limit. Okay? And then they go back and plug it in and show that it is indeed epsilon or less than it. Okay. Which is kind of back. Now, that's the easy one. Let's do the harder one. A new one is coming up here. Okay. And these kind of drive me nuts sometimes because usually they're easy to do, but then much harder to prove. Yeah, this one is. Prove that the limit as x approaches 2 of x squared is 4. Yes? I'm sorry? I can't hear. Oh, this is example 8 in the text on page 58. Bottom of page 58. Okay. Now, using my first technique, plug it in. Obvious, that's the answer, right? All right. Now, here we go to try to prove that. Okay? Start this way, always. Let epsilon be greater than 0. Then, there is a delta, or if epsilon is greater than 0, there is a delta also greater than 0, such that, that colon shorthand is such that, for any time absolute value of x squared minus 4 is less than epsilon, there is a delta such that 0 is less than absolute value of x minus 2 is less than delta. I can't write. Okay. So, that's what we're going for. Here we hit a problem. Okay? What you reckon we're going to do? What would be a good first step here? Factor. All right, he's got it down. Okay? That would be x plus 2 times x minus 2. That's less than, I always want to put equals there. It doesn't need an equal. Okay. It's less than epsilon. That's what we're given. Okay. Whoops. Forget my absolute value one. All right. Now, before it was real easy to factor out a constant if it's positive, right? No guarantee either one of these are positive. Now, sure, as x is approaching 2, you can make sure that you're going to stay positive. Just keep it less than 2. You know, your the epsilon less than the delta less than 2. Let's say it that way. Then that makes this positive, but that doesn't guarantee this will be positive. It may not be. Okay, so you can't just do it as straightforwardly as before. Okay. Now, so to find the appropriate delta, we start by doing just what we did, only we're going to take it one more step. This is actually, I wish I had written this elsewhere, x plus 2 times the absolute value of x minus 2. Okay, now, there is a theorem somewhere out there that the product of the absolute value of the product is always less than or equal to the product of the absolute values. That is a rule out there. I don't know if they name it here. Sometimes they call it the triangle theorem or something like that, or they have names for it. But that's true. You take my word for it, it is. Okay. Obviously, the absolute value of the product has to be less than or equal to the product of the absolute values. Okay? One of these could be negative and one positive, and that could come out being a negative number here, but you take the absolute value and it's positive. Here, they're both guaranteed to be positive, and so it's going to be less than or equal to that. So we're okay with that. All right. Now, since we're interested in x values, this is what I was saying before, close to 2. X is approaching 2. Okay? Let's choose an x on an interval between 1 and 3. Okay? Well, let's choose an s. This is where it almost gets Weasley, it seems like to me. Let's choose an x on the interval from, I've got his knee, sorry. Y'all awake yet? Okay, good. All right. On the interval 1 to 3. Okay? Now, remember we want this close to. So we can say, yeah, that's going to be close enough. You could have even said 0 to 4 if you wanted to, but 1 to 3, that's even better. Okay? So if you want it close to 2, 1 to 3 is certainly going to cover that well. Okay? Now, this is not necessarily positive. This is guaranteed to be positive. 1 plus 2 is 3, and 3 plus 2 is 5. Both of those are positive numbers. Okay? The larger of them being 5. Okay? So we're going to focus on the larger one then, because we want something less than. So what we'll do, and this is what they're doing in the book. I'm trying to make sure I don't skip any steps for you here. Everything on that interval, x plus 2 is going to be less than 5. So if we do 5 times the absolute value of x minus 2, that's going to be less than epsilon. Okay, because epsilon is some small number. doesn't quite seem like that's fair to do. Okay. Let's back off. I did skip a step there, so let me... Oops, that one's fine, but this one's not. Okay. And this gets sort of tedious. Okay. What we want to do is guarantee that the absolute value of x plus 2, okay, we know that's going to be less than 5. If you're any x on this interval, this is going to go from 3 to 5. So therefore, every value that this do, if you keep it within that, then that's going to be less than 5. You guarantee, okay? Because this is an open, remember, open interval. So it can't be 3 and it can't be 1. So therefore, it's got to be less than 5. Okay. So, now, if that were the case, we now have two choices for delta, okay? And here they just sort of, so letting delta be the minimum of, okay, and in other math books and stuff, they introduce a function called the minimum function. Whatever is in here, you take the lesser of the two values. They don't bother with that here. They just say it. Let delta be less than, or be the minimum of, either here, if whatever this is, you know, this part has got to be 5, so let that be the minimum of epsilon over 5. You just divide epsilon by 5. That would be the greatest case. Or, on the other hand, 1, okay? The minimum of that or 1, whichever is less, okay? Now, you might say, okay, where did the 1 come from, okay? Well, if you have the x in that interval there, this one's 5, and this would be, okay, let's choose first the left-hand side. This would be 3, and this would be a -1, so absolute value would be 1. So that's okay. If you choose it to be 3, the upper bound, this would be 5, and this would be 1. So if you choose that to be close to 3, you know, as close as you can get to 3, then this has to be less than, that would be 1, so this would be less than 5, and that would be less than epsilon, okay? Because this part here would be absolute value of 1, okay, if you're in that interval, okay? So therefore, I'm sorry, I wrote x, it should be epsilon. So therefore, divide both sides by that, and that's where you get the epsilon over 5, okay? Now, where did the 1 come from? That would be if you had the lower limit, and the lower limit there would be 3 times a, oh wait, sorry, I skipped one. To satisfy that restriction, what we're going to do, and I forgot this part, and this is one I missed, and that's why I kept saying, where is this coming from? We're going to say delta has got to be less than 1. They just threw that in there, delta less than 1, okay? That's going to be the first, okay? So this gives us then, it's going to be the minimum, that's where you get this one from. Choose a x there and say, just pick some value, okay? And to satisfy this equation, okay, you're interested in the values x close to 2, so you choose at x in the interval 1 to 3. To satisfy that restriction, let delta be less than 1. Well, yeah, that's a fairly reasonable. And then from the rest of it, if you're in that interval, then everything else has to be less than 5. Okay? So basically 1 is this end, or that the delta is less than 1, or the delta is less than the maximum value, which is epsilon over 5. Okay. Now, obviously the epsilon over 5, if you let epsilon get small enough, it's going to be less than 1. So that's the one you have to worry with. So, you're going back to this one, okay, and you plug in the absolute value of x minus 2, they wrote them in different order, absolute value of x minus 2 times the absolute value of x plus 2, okay? If you plug this in, this is less than epsilon. We know that's got to be the case. Well, this one right here, that will produce, if they wrote them in the right order here, if it's 1, this is going to be, I'm sorry, if it's 1, this is going to be epsilon over 5. And if it's 3, then this is going to be 5. And then the product of these two, the 5's cancel out, and you get epsilon. And it looks like circular reasoning to me. It's really painful to go through in my mind. What I say, plug it in. If you get something that's an answer, that's your answer. If you get something that's indeterminate, then you have to pursue it further. And we'll use some analytic techniques to do that if necessary. If you get something that's absolutely not allowed, it's not going to work. Okay? So I'm not going to require you to do that many proofs with this. If we do them, they're going to be the fairly simple ones. Okay? I'll just leave it like that. Homework exercises. That finishes 1.2. Do any of the odds 5 through 9. They're all at calcchat.com. All the answers are in the back of the book, but they're all at calcchat.com. Number 5's at calcview.com. Then do any of the odds 11 through 17. They're all at calcchat.com. And by the way, here you'll have to use some of your more analytic techniques. Well, no, they want you to use numerically. If you can't do that, or if you find it really awkward, try some analytic techniques. That's okay. Do number 19. I think you can do that right off the top. Okay, do any of the odds 21 through 27. They're all at CalcChat. 23's at CalcView. Do 29. It's at CalcChat and CalcView. Do 31. It's at CalcChat and CalcView. Do 33. It's at CalcChat, but not at CalcView. And then do any of the odds 35 through either 35 or 37, both at CalcChat. Then using the formal definition or whatever you choose to use, any of the odds 39 to 43, they're all three at CalcChat, 41's at CalcView. Any of the odds 45 to 55, they're all at CalcChat, 47's at CalcView. Try doing 57, 59, they're both at CalcChat, or should be. 61, it should be at CalcChat. The 63 or 65 are both what they call exploring concepts. So take a look at those, explore them to your heart's content. But you don't have to do anything. 67 should be one you could do. And by the way, they should be at CalcChat too. 67 you probably can do. and 69 should be at Calc Chat. These are getting a lot more esoteric, so don't get bogged down with them. Look at Calc Chat, see if you understand what they're dealing with. Graphical reasoning, you're welcome to try 71. If you get too bogged down there, go to Calc Chat. Now, they give usually some true-false. I don't really care for true-false. You're not going to get any true-false on the test from me, because I hate true-false questions, because you can have one little word or emphasis here. That's what's messing you up, but you focus on something else, and everything you're focusing on, you're right, but this one little thing you kind of didn't quite see, that could be a possibility here. So that, to me, is not proving anything, okay? So, but still not a bad idea to look at 73 and 75, especially using Calc Chat. Then 78, same thing. 79, the same thing. They should both be at Calc Chat. Now, beginning with 81 and 83 are both proofs. And if any of you math majors as opposed to pre-engineering. Now, I know some of you have changed to be math majors, but your plans are not to stay as a math major, right? Okay, if any of you are planning to continue as a math major, they're the ones that are going to require more proofs than the engineering field will. So I'll let you decide. They're not hard, but I'll let you decide where you're going to put your emphasis. Okay, and then 85 is the Putnam Challenge, which usually are pretty difficult. If you want to look at that, I hope that's a Calc Chat too. You may find some benefit in looking at it. Any questions? Okay, let's move on to 1.3. And guess what? I forgot to bring my watch in again today. I just got to take it out of my coat pocket and put it in my pants pocket, but I forget to. I broke the pin on it, and I haven't gotten that repaired yet. So let's end this and go to 1.3. All right. I know this is what Bill's been waiting for. Evaluating limits analytically. That's a lot more fun to me than either numerically or graphically, or certainly by a formal definition. So let's go to the current slide. All right. Evaluating limits analytically, 1.3. We'll evaluate a limit using the properties of limits. So we're going to first learn the properties of limits and then use those to evaluate limits. We'll develop and use a strategy for finding limits. That sounds good to me. Evaluate a limit using dividing out technique, which I think we did earlier. Rationalizing, I know we did the rationalizing earlier. And evaluate a limit using the squeeze theorem, which is rather bizarre but true, but to me seems awfully limited in its application, but when you can use it, it can help you with some really hard problems. Okay, so let's start with the properties of limits. The limit of f of x as x approaches c does not depend on the value of f at c. That sounds bizarre, doesn't it? But remember those strange little problems we did? F of x was doing this here and that there, but at c is down here. Well, the limit is up here. The value is down there. Now, you don't have very many things in real life that do that. But if you ever did, the limit exists, but it may not be the value at x equals c. So that's the problem with plugging in. If you have a piecewise defined function, be very careful plugging in. If it's just a regular old function, plug into your heart's content. Only the piecewise defined functions will you find that be, I think that's going to be an issue. It may happen, however, that the limit is precisely f of c. That's why I say plug it into c. In such cases, we can evaluate the limit by direct substitution. The Glade technique, plug it in. So that's the first attempt. Plug in x equals c and see what you get. Now, I think probably most of you could think of this if you thought deeply enough about it. There could be some that do have this very thing I'm talking about, except they don't have a value here. They're just not defined at x equals c. and we'll hit some of those, so I won't spoil it for you. Such well-behaved functions, and we like well-behaved functions, don't we? They are continuous at C. If a function is continuous at C, it's going to have a limit at C. So there's a theorem right there. Well, not yet, but this is true. Okay, got that. If B and C are real numbers and N is any positive integer, here are some things that are always true. Now this almost seems to be in such a duh category that you think, why do you even say it? But it is necessary to say. The limit of the number B as x approaches C is that number B. Whoa, what are you talking about here? If x equal B is your function, right? What is that function? X equal B. A constant function, right? So if x is -7, it's B. If it's positive 12, it's B. If it's pi halves, it's B. If it's 0, it's B. So in other words, the limit of a constant function is whatever its value is. No matter what you're approaching, x approaching anything, if it's a constant function, the value is B, right? It's a constant function. All right. Now, the limit of the function f of x equal x as x approaches C is C. Now, why is that? What does this function look like? It has a special name. This is too. That's a constant function. This has a special name. Anyone remember it? F of x equal x. The what?
Parent function.
One more time.
Parent function.
Okay, it is a parent function sometimes called. It has a more specific name. Let's say y is equal to x.
Linear.
It doesn't have to be linear. It is linear, you're right. It doesn't have to be an integer. Y is equal to x. How does it graph? Tell me that. Okay? I knew I brought this up for some reason. Y is equal to x. Give me an x. Any x. 2. Okay? And there's your x. What would y be if y is equal to x? 2. There it is. Okay? Give me another x. Second? 6. Okay? 1, 2, 3, 4, 5, 6. What would the y be if y is equal to x? 6. Okay? Give me another x.
10.
Second? 10. Okay? That's 6, 7, 8, 9, 10. It'd be 3, 4, 5, 6, 7, 8, 9, 10. Okay? Have I gotten off here? Yes, I did. 1, 2, 3, 4. There it is. Okay. Yeah. Okay. Give me a negative x. -2. Okay. What would the y be? -2. Y'all left off my favorite. 0, 0. Okay. That's what I worn out there. Okay. You see what function this is? Anyone remember the name of it?
Is it even?
Second?
Even function?
No, actually, it's an odd function because whatever you're doing here, you go the opposite way there. This is called the identity function. Whatever the x is, that's what the y is. They're identically the same. So there it is, the identity function. Okay? Now, as x is approaching C, give me a C, any C.
4.
4. Okay, 1, 2, 3, 4. As x is approaching 4, either from left or right, what is the y approaching? If I were going to the right place. It's approaching 4 too, isn't it? Because it's the identity function. It's approaching itself. So this is saying that the limit as x of the function x, as x approaches C, plug it in, okay? X equals C, C is equal to C, that's equal to C, okay? There is the thing, okay? It's the identity function. Whatever x is approaching, that's the limit. The y is approaching that same C. All right, and then they put this one in here. Remember, n is any positive integer, and frankly, it would work for negative integers as well. The only integer it wouldn't work for is 0. Okay. But for positive integers now, we'll leave it alone. The limit as x approaches of x to the nth, that's the power function, x to the nth, as x approaches c would be, plug it in, c to the nth. Okay? So there we have it. Those are the three they're going to give us without telling us anything else. Those are true. The limit of a constant is the constant. The limit of x as x approaches c is whatever c is, okay, because that's what it is. And the limit of a power function as x to the nth, as n is any fixed positive integer. Oh, positive integer. It's not fractions or decimals. We're not going there yet, okay? Then that will be c to the n, okay? So with those three in our belt, we're ready to look at some more. So let's do this one. Oh man, I hate when they do this. Okay. What is the limit of 3 as x approaches 2? 3, because it's a constant function, it's always 3, no matter what x is approaching. Okay? I don't know why they write down the answer. Okay, what's this one? Limit of x as x approaches minus 4 of x would be minus 4, because as x goes, just plug it in. It's right there. Okay? And this one, the limit as, you can read my hand, can't you? The limit as x approaches 2 of x squared is 4. You got it. 2 squared, which is 4. Okay. Boy, that was a tough set of exercises. You want some of those on your test? No, they're too hard. Okay, I wouldn't think of it. All right. So that gives us our basics. Now let's go to some other properties. Let B and C be any real numbers. Okay? Numbers, any constant, real numbers. N be any positive integers. So these can be fractions, decimal, rational, irrational, it doesn't matter. N, though, positive integers. F and G be functions with these limits. The limit as x approaches c of f of x is L, and the limit as x approaches c of g of x is some number k. And like you asked before, these are just some constant numbers, L and k. So, here's the first property of a limit, the scalar multiple. What is the limit as x approaches c of some scalar number, b, any number, real number, rational, irrational, just any real number, of that number times f of x, okay? Well, if this is just a number, you can pull it outside the limit, and then the limit as x approaches c of f of x is L. So this would just be b times L. Okay. Hopefully that's what you would expect it to be, and that's what it is. Now, certainly b could not be a variable, then you can't do this. But if b is a number, a constant, just pull it out, and it's b times L. Okay? Now, sum and difference. The limit as x approaches c of f of x plus or minus g of x would be, and here's the sort of rhythmic way of saying that. The limit of a sum or a difference is the sum or the difference of the limits. In other words, split this into 2. This would be limit as x approaches c of f of x plus or minus the limit as x approaches c of g of x. The limit of x approaches c of f of x is L. So that'd be L plus or minus the limit as x approaches c of g of x is k. So that'd be L plus or minus k. Hopefully, just what you would expect it to be. Right? Pretty exciting stuff. Okay. Now, the product of a limit. The limit of a product is x approaches c of f of x times g of x. Guess what? That's the product of the limits. The limit of f of x is L. The limit of g of x is k. So the limit of the product is the product of the limits, which is L times k. Okay. Don't know if you're expecting that, but that's what it would be. Basically, plug it in. Limit of a quotient. This is the one that always, when you give a quotient, you have this little caveat you have to say. The limit as x approaches c of f of x over g of x would be the limit of f of x, which is L, divided by the limit of g of x, which is k. That's only true if k is not equal to 0. if g of c is 0, that's a perfectly good thing for it to be, but then this doesn't have a limit because you'd be dividing by 0. Some number divided by 0. Can't happen. If that L was a 0, also, then that may be an indeterminate form, so you might have to do some other stuff to check. And then the power, this time it's not f of x being the power function, but you're raising f of x to a power, and it's just like you would expect, I hope. The limit of a power is the power of the limit, okay? The limit as x approaches c of f of x raised to the nth power. I would usually put that f superscript n of x, meaning raise that to the power. That would then be the limit raised to that power. Those all seem like they should be kind of intuitively obvious, mathematicians like to say. I don't know if they are to you, but they certainly are true. All right, now they give one that we can actually do. Okay? Find the limit as x approaches 2 of 4x squared plus 3. Now, I bet you they're going to drag it out in gory detail. But if you want to do it simple, you can. What would you do? Plug it in, plug it in. I like it. Y'all have been influenced by somebody. Okay, never mind. Okay, and what would that give you? 19. You got it. 4 times 2 squared. 2 squared is 4. 4 times 4 is 16. Plus 3 is 19. Done. Now, I'm sure what they're going to do, or I suspect what they're going to do, is say the limit as x approaches 2 of 4x squared plus the limit as x approaches 2 of 3, and you do, and then say, oh, but this is the same as 4 times the limit as x approaches 2 of x squared. Yeah, you could do all those steps if you wanted to, but goodness gracious, it's just plugging it in. That's all you're doing. So you can use the shortcuts if you want to. I mean, after a while, everybody will be doing that, but to begin with, they sort of want you to think through all that, I guess. I don't know. All right. It's 19. Okay. Let's erase this, and I'll show you. That's what they were planning to do. Okay, sorry about that. What's that? I'm sorry, I can't hear you. Okay, my hearing is terrible. I need to get a hearing aid, and I'm just either too vain, too lazy, too cheap, or something. I don't do it. I've got to get one. Okay, and just like I told you, they split it, the sum, into the limit of a sum is the sum of the limits. And then they say the limit of a constant times a function is the constant times the limit of the function. And this just stays the limit of 3. And then this will be the limit of 4 times the limit of 2 squared. I bet you they put that step in. Yes, they do. 4 times 2 squared plus 3, and that gives you 19. Okay. Y'all did it in one step. Okay, good for you. Okay. But it works. And this is using each of those properties of limits that they list over there. Okay, after a while, you just do them. You don't even think, oh, this is that property. Okay. All right, that limit is reinforced by the graph of f of x equal 4x squared plus 3. We know that function is a parabola that's been a vertical shift upward by 3. That's what the plus 3 does. The 4 is a vertical stretch, so you stretch those things, and that then gives you, when you plug in a 2, you get a 19. Okay? Yeah, we figured it. It gave it to us without having to graph it. Thank goodness. Okay. All right. All right. So that function we just did was a polynomial function. So the limit as x approaches 2 of a polynomial function, that function we just did, is simply the value of that polynomial at x equal 2. Now, this is requiring you to think back to some things we said earlier, okay, and things you hopefully learned earlier. What is true about polynomial functions? There's two characteristics that are true of any polynomial function. Polynomial functions are, and we're not going to use this one now, smooth. Think jazz. Okay. They're smooth. Okay. The one that we're focusing on now, they're continuous. Remember way back there was a little phrase there, if it's a continuous function, you just plug it in. So since polynomial functions are always continuous functions, always defined for all real numbers, that's the key of polynomial function, you can always just plug it in. So to simply put, as the value of that polynomial at x equal 2, just plugging it in, and I think that's what y'all did, wasn't it? Just plugged it in. This direct substitution property is valid for all polynomial and rational functions with non-zero denominators. Rational functions are ratios of two polynomials. That's what the rational function is. As long as that denominator is not 0, then you can plug it in, plug it in. If that ratio is 0, then we'll be using other techniques to try to eliminate that. So let's do it. So here's theorem 1.3. Limits of polynomial and rational functions. If p is a polynomial function, c is a real number, then the limit as x approaches c of p of x is simply p of c. Just what we were just saying. And if r is a rational function given by r of x is equal to p of x, which is a polynomial function, divided by q of x, which is another polynomial function, then c, and c is a real number, then q of c, okay, and q of c, a real number such that q of c is not equal to 0, then the limit as x approaches c of r of x would be r of c, which is p of c divided by q of c. As long as that q of c is not 0, plug it in, plug it in. If you wind up with a 0 in the denominator, you can't use this. But if you don't, you're perfectly fine. Okay? Everybody got it? I'll let you. If you're writing, I'll let you write it. Our earlier example was one of a polynomial function, the last example. Now we'll do one next of a rational function, which is pretty easy, straightforward. Those are some little bless yous there. Those are so small sneezes. Okay, all right. I don't go for little ones. Mine are loud and obnoxious. Just, well, thinking of it now, remember, I think I told you last time, all your PowerPoints are out there on Blackboard, all your everything is. Keep reminding myself I got to check one class. I put the wrong syllabus out, but this one is correct, I think. There are some advantages to the old days. Like I'm thinking back when I took this, they didn't have computers, projectors, PowerPoint, or anything like that. So the prof was writing everything out. You could almost just keep up with them. But now it's there, and you have a lot of catching up to do. So sorry about that. It's easier on me though, so I'm not that sorry. Okay, I'm pretty sorry. Oh, I did want to rub this in a little bit. Yesterday, it was actually the first day I met with my Tuesday, Thursday classes, because the first Thursday I was at the surgery center where my wife was having outpatient surgery. But someone else met with them, got the role, but all the information was there. Yesterday, the first day I met with the class, one of those obnoxious students turned in his research paper. Yeah, you wanted to hear that, didn't you? Okay. All righty. I've gotten one research paper in. I went, all right. Okay. And I hadn't even met with the class yet, and he had already gotten it done. Okay. Hint. Okay. Never mind. Anytime. I'll take them anytime, folks. Be very happy. Okay. So let's do example 3 here. Okay. The limits of a rational function. What do you think you would do? Anyone want to hazard a guess? Plug it in. And what would that give you?
2.
Okay, 1 plus 1 plus 2 over 2 equal 4 over 2, 2. Perfect. Y'all are good. Why does that work? Because 2 is not equal to 0. Okay, that denominator is not equal to 0. So it works perfectly well. All right. But can you imagine some place where that rational function is not defined? Second? -1. X equals -1. You can't do what we just did. Okay. You could do it for any other x. X equals 1.00001. Yeah, it would be, or 0.9999999. You can still plug it in. But x equals negative, I should have been saying that. X equals -1, can't do it. And there's not much way around it either. You just can't do it. Okay. At that place, it would not have a limit. Okay. What's that? I can't hear. Is it time? Oh, 7 minutes? Is that what you're saying? Okay, good. Thank you. Okay, let's see how they did it. I don't think I have to even erase anything. Because the denominator is not 0 when x equals 1, you can apply theorem 1.3 and obtain 4 over 2, which is 2. And there's your function. Now, I think you can probably almost see where the problems would come. They did draw the other half. At x equals -1 here, notice that thing's heading up awfully sharply. That's approaching -1 is a vertical asymptote. You're never going to have a value there. Okay? So we won't have a limit there. Now, we haven't done these yet, but I'll almost guarantee you on the other side of -1, it's going to come like this and go like this. Now, that has a vertical asymptote at -1, so there is no value, no limit there at all. Okay. Now, the other thing about this, anytime you have a rational function whose numerator is exactly 1 degree more than the denominator, this is a quadratic, degree 2, that's degree 1, then you're going to have what we call a slant asymptote. You have a vertical, a straight line that forms your second. If this had been exactly the same, an x squared here and x squared there, you would have a horizontal asymptote. Okay, but if this is 1 more degree than that, you're going to have a slant asymptote. You don't have to know that. That doesn't bother what we're doing here. It does. It is affected by the fact that x can't equal -1. Vertical asymptote there. A little bit of review of pre-calculus algebra there. Okay. Now, Okay. Polynomial functions and rational functions are two of the three basic types of algebraic functions. What's the third? Okay. One that involves a radical. Okay. So we need another theorem for that. The limit of a function that involves a radical if n is a positive integer. Remember that, positive integer. The limit below is valid for all c when n is odd, and is valid for c greater than 0 when n is even. Okay? This is stuff you probably remember from back pre-calculus algebra or wherever when you did radicals. The limit is x approaches c of the nth root of x. Now that, what's another way to write that? Right now, nth root of x is perfectly fine. In the future, though, you'll write that in another way. X to the 1 over n. Perfect. I far prefer that for most cases in calculus, but this is okay for now. Well, if that n is, it has to be positive. We don't ever deal with indices of a radical which are negative. Ugh, don't even go there. So n has to be positive, okay? Can't even be 0. We don't deal with that either. In fact, we usually don't have n equal 1 because the nth root, the first root of x is just x. So we don't even mess with that. So it's n 2 or greater, okay? If n is even, that requires c to be positive. You cannot take an even root of a negative number, okay? If n is odd, though, c could be any real value, any value, and this will be true. So if n is even, c is required to be positive. It could be 0, okay? C could be 0. That would be all right. They say c greater than 0 when n is even. It could be 0 when n is even, but we'll leave it greater than. But if n is odd, c could be any value in the world. A proof of this theorem is given in Appendix A. I know you want to get back there and see it. All right, how are we doing on time? 3 minutes. All right, I think we have time to do this one. This next theorem greatly expands your ability to evaluate limits because it shows how to analyze the limit of a composite function. Y'all remember what composite functions were? F of g of x, that type of thing. Your argument of the first function is not a number, but is another function. Okay. So the limit of a composite function, f and g are both functions, such that the limit as x approaches c of g of x is equal to L, okay? And the limit of f of x as x approaches L is f of L. Oh, that makes sense. Then the limit as x approaches c of f of g of x would be the f of the limit of x approaches c of g of x, which we know that to be L, and that would be f of L. Okay. Seems like they are beating a dead horse, but it really works, okay? The thing is, f has to be defined at the value for g, the value of g at the function. That's basically all it's saying, okay? Now, I don't know if we're going to have time for the example, are we? No. Oh, Jake always says no. Okay, we'll pick up next time. Yes? Oh, I'm sorry. Yeah. We'll pick up next time at example 4, I believe it was. Let me just sneak a peek and then I'll go right there. Yeah, we'll start next time at example 4. Let me give you a few more homework exercises. I know you want those. You don't want to leave home without them. You can do some of the odds, 5 through 21. They're all at Calc Chat. 7's at Calc View. Do either 23 or 25. They're both at Calc Chat. 25's at Calc View. And we'll stop there. We'll pick up the rest of those later. Okay. In fact, on 23 and 25, you can do the first A and B parts if you want to hang off and not do C until we do those examples, you can do that as well. Good deal. Yes, sir.
What page is it?
The homework. The first set in 1.2 was on pages 59 through 62, and the ones I just assigned out of 1.3 were all on one page, and that was page 71. Any of the odds 5 through 21, and 23 or 25, the A and B parts, but not the C.
Thank you very much.
All right, that's it.
You have a great day.
What's that?
You have a great day.
All right, you too. Thank you.
I have a
Yes,
problem
sir.
keeping up with the Cal chat and so forth like they did these, but the book cut off, or, you know, we
Right.
talked about that,
Right.
that the problem sets are not,
Not exactly equivalent, right?
yeah, so I'm going to have to buy the book just so.
Okay. I was going to ask, have you checked to see if it's in yet?
It's in now.
Oh, it is. Okay.
So I said I was going to,
Yeah.
do you want these? Or
No,
the
no,
whole-
those are for your cultural enlightenment,
Okay,
your
now,
practice. Yeah.
now I got to go over this thing. You're saying Cal chat, and I'm not understanding Cal chat.
Okay. Well, I think it was in that book too, but when you see the homework exercises, wait, let
I
me,
see them, but it just don't add up.
okay, wait, let me put something in here. Probably the wrong thing to put here, but I'm going to put it there, just so I know where I left off last time. Oh yeah, you see that here at the top, calcchat.com. Okay, the other one is calcview, VIEW.com. Those are the ones that have the red letters.
Okay.
Yeah.
Cal chat is just a
Calc,
normal.
CalcChat does the odd number exercises.
Okay. I hope I got it right.
Okay.
And I think I just better just go and buy the book because I can't
Yeah.
keep flipping back and
Right.
forth like
I'm
that.
sorry, but at least
Okay.
it got you started anyway.
Okay, I think I should turn this in.
Okay. Yes, sir.
Can I use you as a recommendation for Honors College?
Say this again.
Could I use you as a recommendation for all Honors College?
Do I give them? Is
Yeah.
that what you were asking? Yeah, if I feel like the student deserves it. Yes, of course I will. Do you need one?
Yes, sir.
Okay. When do you need it by?
Just whenever.
Okay. All right. I have almost no time today.
Okay.
I may have some time. Wait. Today's Wednesday. Yeah. I have almost no time tomorrow. But I may have time on Friday unless something big has exploded over the Birmingham campus. So, so I'll try to get it done Friday if I can.
All right.
Okay. And if not, next week, remind me again, because Monday I do have 2 hours at the end of the day, so I can work on it then.
All right.
Okay.
Thank you.
All right. Glad you're doing it. How about math team?
All right.
Consider that now, because you'd be excellent.
Let's see.
Okay.
Okay, you want me to drop this off in the office?
I can take it, so you don't have to
Might
carry
be
it.
a little heavy for you.
Yeah, but you see, I'll leave this up here because my next class is also this Cal 3. So I'll be going down there and not carrying anything.
I hate to spend this $200, but
Oh, yuck.
I gotta try to keep up in the right fashion.
Okay. If you
I
wanted
don't think
to,
there's that much difference. It's
Yeah.
just that they have to do something to make the edition sellable.
right,
You know, something has to be different.
right. I was just trying to think. If you did that Cengage Unlimited, that's only $119, $120. And then once I get the other thing done for $8 more, you can get a copy of the book, but you have to turn it in at the end of the term. Are you planning just doing this course, or are you thinking of doing the whole sequence?
I'm going to try to do the whole sequence.
Okay, well then it probably will be, if you don't want to mess with it, Cengage Unlimited, you can, it'll be cheaper to buy the book than pay for that 3 times. So, because then it'd be 120, 120, 120.
I was trying to think of something else. Okay, I'm